Welcome back, everyone. So today, we finally capitalize on everything we have done so far over the last several lectures, and especially the last two lectures on the angular momentum, in order to develop our full quantum theory for the hydrogen atom. So we do our first step in atomic physics, if you want. So let me remind you very briefly what was the general architecture of our approach that we followed when we wanted to discuss the classical theory of the hydrogen atom. So we began by noting that trying to solve the Schrödinger equation for, well, we kept the nucleus fixed in the middle and we forget about its motion. That can be corrected, but let's not worry about that here. And in principle, we would have had like 2, 3 Newton's equation, where, in principle, I would have had the gradient of the Coulomb potential with respect to each coordinate, and you would have had to solve this complicated set of coupled differential equations, and we decided that this was far too hard, and there was no way we could do it analytically. So instead of attempting the strategy based on directly solving the equations in motion, what we did, maybe I completely erased the board, was to take advantage of the fact that in the central potential there is energy conservation. And energy conservation, to exploit for the energy conservation, we express the energy as a kinetic energy plus a potential energy. Let me call it X. And then we made use of angular momentum conservation and realized that the energy, if you go to polar coordinates to account for the fact that the potential actually depends on X only through the modulus root of X. This is a vector of X position, also called R if you want, and this is the X coordinate. They do not represent the same symbol. You can call it X1, X2, X3 if you want to avoid any confusion. But the point here that I want to emphasize is that we noted the potential, the Coulomb potential was a central potential. That implied also not only energy conservation, but angular momentum conservation. And then by going to polar coordinates, you maximally capitalize on the symmetry of the potential, because since the potential doesn't depend on the angles, you only have a function of the distance. And what we noticed is that the kinetic energy could be written in a simplified form, which involve only the time derivative of the radius and the potential, and the angular part of this kinetic energy could have been written in this form, which looks like a potential. And everything that concerns rotation is effectively included in a constant parameter, L square, which is defined at the beginning of the motion and tells you if the particle is trying, if the electron is trying to go through the center of the nucleus, in which case it will have a very small L square, or it's orbitating, forming wide orbits around the nucleus, in which case we'll have a large L square. So this is the angular motion was entirely encapsulated into this fixed parameter. And this, once you fix this parameter, this quantity here has the structure of a potential. We call it the effective potential. So basically, this discussion was showing how a potentially three-dimensional and deadly difficult problem could have been translated into an effective one-dimensional problem in the radial distance by focusing on the energy and exploiting angular momentum conservation. Now, when it comes to the quantum theory of the hydrogen atom, we want to do exactly the same strategy. We want to follow the same strategy because this strategy is based on concepts that remain true even in quantum mechanics. In particular, it is still true that the Hamiltonian is conserved, the energy is conserved, and that angular momentum is conserved because in the central potential, note that in a central potential, for a central potential, the square of the orbital angular momentum operator and the Hamiltonian commute. That's a fundamental result. Why is this true? Well, this is true because, first of all, the kinetic energy and the orbital angular momentum commute. How do I know? Because the kinetic energy depends on the Laplacian, right? Which in polar coordinates has a structure that is basically the same as the orbital angular momentum. Let me show you. You go on the notes, which I discussed last time, provided I can find them, because lately I'm having difficulty navigating in this. So, okay, let's go this way. If you look at the expression of the Laplacian in polar coordinates, it contains this combination here. So there's a part that depends on the angle, and there's a part that depends on the radius. Now, the part that depends on the angle, which is written here, is exactly the same that occurs in the orbital angular momentum in polar coordinates. So clearly, this part of the Laplacian will commute with R squared because it's basically the commutation between an operator and itself. Conversely, this part will commute with this because the derivative here acts on completely different variables. So there's nothing that they can interfere between them. So in other words, when I write down in polar coordinate this, I have a part that depends on R, which obviously commutes with the angular momentum because the angular momentum only involves derivatives with respect to theta and phi. And there's a part that depends on theta and phi, which obviously commutes with the angular momentum because basically it's the same operator up to a term h bar squared, which nevertheless occurs when you write down the kinetic energy. So the kinetic energy commutes with the orbital angular momentum. And the potential energy commutes. Why? Because the potential energy depends only on position and the angular momentum squared depends on angles. And for the same reason as before, they commute. So what does it mean that the Hamiltonian commutes with the square of the orbital angular momentum? Simply that I can find, if I prepare my system in an eigenstates of energy, it will also be an eigenstates of angular momentum squared. So it will be a hyperharmonical spherical. And if I propagate in time, it will remain the same eigenstate. That's what commutation relationship in eigenstate means, right? The eigenstates of the Hamiltonian will remain over time eigenstates of the Hamiltonian, meaning that if the Hamiltonian and the square of the angular momentum operator have a joint eigenbasis, then clearly the time evolution will not change the state of the system. So if you are in a given angular momentum state, you'll remain in that angular momentum state. So yes, angular momentum is conserved even in quantum mechanics for this problem. And the second important point here is that when I write the angular, now let me be more specific and do exactly the same that we did for, remember, when we wrote the classical energy in terms of radial kinetic energy plus an angular kinetic energy, which we rewrote at a square over 2mr squared plus a potential. Now, at a quantum level, we write the Laplacian operator. So let me show. We write the Laplacian operator plus the potential operator, and the Laplacian operator can be written essentially using this equation here as negative h bar squared over 2m, 1 over r, v squared by dr squared r, whatever comes next, negative h squared over 2m squared, l squared r squared. Right? Because this is, again, this is basically L squared. So you begin, plus of course I have my potential energy operator. So now you begin to see there is a one-to-one correspondence to what we did before. Let me copy this and say that, you know, we have 1 over h bar squared over 2m times something that looks like whatever it is, but it plays the role of a kinetic energy operator along the radial direction, plus the square of the angular momentum operator, plus the potential energy operator. So you see, we are basically copying down the same ideas. Now we want to use the fact that the angular momentum is conserved, which means that the energy eigenstates and the angular momentum eigenstates are the same. You know, you can find a joint set of eigenstates, so the eigenstates of both. Of course, the eigenstates of the Hamiltonian also contain the dependence on the position, while the eigenstates of the angular momentum only depend on theta and phi. So, this means that the wave function psi, which is a function in general of r, theta, and phi, can be written as a wave function, as a function of r times spherical harmonic. This is a set of quantum numbers, of course, that we call big N, the quantum numbers, and big N is actually one quantum number for the radial motion, the angular momentum quantum number, and the projection quantum number. So the fact that you can write the wave function in this form follows from the fact that the Hamiltonian and this commute. Okay, so now I want to use this fact, take the Hamiltonian, write down this combination, and see what happens. Well, let's be specific. This is a radial part plus L squared times 2mr squared plus u of r. And when I apply this to r times y, Lm, what I get is, well, let's first apply this. This only acts on r, right? So, because this kinetic energy operator does not involve derivatives over angles. So basically what I get is minus h bar squared 2m 1 over r d by dr squared r times r times y. And now let's continue. When this term here acts on this, it will not act on r because the derivative only acts on theta and phi. So what I get is the eigenstates of the spherical harmonics, which are h bar squared L plus 1 2m r squared times r y. Finally, the potential will only be multiplicative. And this will be equal to the total energy times r times y. So, in essence, after taking this ansatz, plugging it into this Hamiltonian, and simply following the consequences of this, we arrive to the following equation. The angular momentum part of the equation cancels out, and we arrive to the equation for the radial part, which I will write now. So the result is something conceptually identical to what we found for the classical theory. The energy in that case was reduced to an expression that only involved positions, and now the Schrödinger equation, the Hamiltonian, the eigenvalue problem from the Schrödinger equation, becomes a Schrödinger equation which only involves derivatives with respect to position. Different angular momentum states reflect themselves by the presence of this effective potential, which is to be summed to a physical potential. So if you want, I can rewrite this equation in the following form. Negative h bar squared divided by 2, 1 over r, d squared by dr squared r plus an effective potential which depends on L, R equals ER, where the effective potential that depends on L knows about the angular momentum state of the system through this parameter, L plus 1, 2, and R squared. So our goal now is going to be solve this equation. It is convenient to rewrite this in a form that looks even closer to the Schrödinger equation in one dimension, and is obtained by making the substitution you find here, replacing R with 1 over R UR. It's just a change of variable. And if you do, your effective Schrödinger equation, let me not write it, let me just state it, becomes this. So we basically have completed the transition to we have completed the analogy with the classical case. We have reduced the three-dimensional Schrödinger problem to an effective one-dimensional Schrödinger problem for a wave function U that has precisely the structure of a one-dimensional Schrödinger equation. And for example, we can use the Schrödinger code that I provided you with to solve the Schrödinger for the ground states of different, to solve for the wave function in different angular momentum states. For instance, basically what we have is where we can classify the eigenstates in terms of the value of the angular momentum. So we will have three sets of quantum numbers. We will have a quantum number n, which will tell me about the radial excitation, which are associated to the Schrödinger equation for the U function, little u function. We will have a quantum number L and a quantum number M. So for instance, these are associated, of course, with quantum angular momentum. So for instance, I can start by saying I'm looking only at solution with L equals 0. Then clearly M will be equal to 0. And then the solutions will come from solving the Schrödinger equation, negative h bar, 2n, second derivative with respect to r squared of my function little u of r. This is my small function. Plus, now I'm going to write explicitly the Coulombian interaction, negative e squared over r squared over r, sorry, r squared, u of r. This is the radial wave function. Remember, r is equal to 1 over r little u. It's a bad notation, but it's an historically used notation. This u is not the potential. This is actually big U of r is the potential. Okay, so I've avoided using big U because, not to generate confusion, I wrote explicitly the Coulomb form, and this should be equal to some energy as U of r. And since I will find in general a quantized solution, I will put my principal quantum number. So this is the equation for the zero angular momentum states, and these are called S states. Why S states? Because when you have zero angular momentum, remember, the spherical harmonic becomes just a constant, a normalization constant, and the wave function is symmetric for around the sphere. So S stands for spherically symmetric states. Then I will have a set of solutions for L equal 1, and I will have three possibilities. And in this case, the Schrödinger equation I have to solve to compute these states will be a different one. So let me encapsulate the Schrödinger equation for each state, and it will be negative h bar 2n d by dr squared u, again, that will be my n principal quantum number, again, that will be my e squared over r u with my principal quantum number n. But this time, I will have also contribution for the effective potential. I will have h bar squared L plus 1 divided by 2m r squared u of n, and this will be equal to e u of n. So clearly, I will have another set of solutions which correspond to finite angular momentum. And for each value of finite angular momentum quantum number L, I will get 3 identical solutions because these equations do not depend on the value of the M quantum number, which simply tells me that states with angular momentum 1 will be triply degenerate because the solution where the orbital angular momentum is +1 projection, the one in which the projection is 0, and the one in which the projection is -1, they will have all the same energy. So there will be 3 states for each value of N and M, and they correspond to 3 different values of N. These are degenerate states, same energy. And then these are called P states. And then you can go on and take L equal 1, go L equal 2. In this case, you will have the same expression, but rather than having 2 here, you will have H bar. Now when L is equal to, this is 2 plus 1 is 3, times 2 is 6, 2mr squared. You get a different equation that will give you different energies, and you will get now 5 different degenerate solutions, and so on and so forth. So you will get, in general, S states. You can classify your energy states in S states, P states, D states, which are angular momentum larger than the 1, and so on and so forth. Now, how do they organize with respect to each other? Well, this is, first of all, we haven't finished our problem. We still need to solve the radial part of the Schrödinger equation. Now, if I solve the radial part of the energy of the Schrödinger equation, I will get the energies of all N states, of all P states, and of all N states. Now, this part is the part that I will not treat, because I gave you a code that can be tweaked to do that numerically. Right? So instead of doing analytically like traditionally was done in the beginning of last century where there were no computers, I will not bother you with solving the complicated hypergeometrical confluent series that horrible mathematical objects. Can simply go pick up our code, and if you look at the code, look at the code at the beginning. Now you make sense of the following. First of all, we're interested only in positive distances because we're not interested in negative distances. Let's say with 10 here. And you see here we have dimension. Now we go and put dimension 3 because we're interested in the 3-dimensional problem for the hydrogen atom, and we choose the angular momentum state. For instance, this is for S states, or I comment this. This would be for P states. Now, when you do that, for instance here, you can write the potential, the physical potential to be negative 1 divided by RB, that's the Coulomb potential. And you see, for D equal to 3, the code will add the angular momentum part in unit of H bar in a system of units when the mass is 1 and H bar is 1. This is called the atomic units. I never mind about it. And then, depending whether you're in what dimension you are, you will solve for the proper eigenvalues. So I recommend you do that and you organize your states accordingly. And if you do that, you can discover what is the ordering of the states. In particular, once you have done all this, you can in principle solve for all the S states, all the P states, all the S states, and then look at the corresponding energy and see which one is the ground state, which one is the first excited state, which one is the second excited state, and so on and so forth. So basically, what I'm going to tell you now is what happens after you have done this. After you have done this, you discover that the ground state of the system is a 1s state, so it's a S wave, which means that in the ground state, the distribution, the probability distribution of the electron is symmetrical around any axis, is basically spherically symmetrical. What about the radial distribution? Well, it comes from taking the square modulus of the radial part of the wave function, and it looks a little bit like this. This is what happens when you plot it, the probability of finding a particle at a given distance from the center of the nucleus. So in a picture, that's how it looks. A hydrogen atom will look like a cloud, a spherically symmetric cloud. Note that the probability of finding the particle in the origin in this hydrogen atom is actually 0. That would be a typical best distance when the system will be found. Now, the first excited state, the next to lowest value of the energy, is not a P wave, is again the second excited state of the zero angular momentum state. So the second energy is again an S state. It's called 2s. 2 stands for the second on the S states. Then you have a P state, and P states now do have dependence on principal theta and phi. But if you go and look, the P states basically, when you draw the probability, you go back and look, you discover that the probability will not depend on phi, so you get spherically symmetric state along the z-axis. And the other states will be symmetrically over the other axis, but these are called P orbitals. So the wave function of P states will look like this. And then you get the third excited state is again an S state. It's again a spherical symmetric. And as you go more forward, you get these states along the spectrum. So again, just as we did for the square box, there's something interesting here. We find that in the quantum theory of the hydrogen atom, the electron cannot be found at certain distances from the origin. For instance, in a 2s state, the electron will never be found at this distance. In the 3s state, it will not be found at these two distances, because that's where the wave function has node and the probability has name, dark spots. So that's it. That's how you describe quantization energy of the hydrogen atom. And you can compute the energy for each of them. Actually, you can do all this completely analytically. And this is an incredible strike of luck, which enabled physicists to prove that quantum mechanics was providing incredible prediction far before the invention of computers. In turn, computers could have never been discovered without quantum mechanics. So basically, without the possibility of testing quantum mechanics in atomic physics, which at the beginning of last century was considered radically important to develop quantum mechanics, to trust quantum mechanics, people probably would have never discovered a computer through which now we can trust quantum mechanics much more because we can solve all problems, much more problems. Anyway, the spectrum and the radial eigenfunctions for these problems can be solved exactly. And therefore, in principle, the hydrogen atom is a completely analytically solvable problem. I will not do that in this course, but I gave you a code through which you can reconstruct all the solutions. And so basically, you also have a complete understanding of the hydrogen atom spectrum and eigenstates at this point. Okay, Next lecture, we go over this material again, try to digest it a little bit more, and then move forward. Bye-bye.